All right, welcome to Advanced Workflows with Durable Functions. I appreciate everyone coming to the last session of the day. I was a little bit concerned about jet lag, but it's actually morning where I'm from, so I'm waking up right now, so it's perfect timing. If you were here about 9 hours ago for the keynote, there was a mention of 1982, sort of a magical year where Mr. Neal was introduced to computers. That's about the same time that this game came out, and it's something that left a huge impression on me. It's a text-based adventure game. You can tell from the packaging, though, they really spun quite a visual there. You can see the sort of skull, you can see the castle, you can see the imagery of the dungeon. And this is when I visited the catacombs in Paris. And it was how I visualized as a kid playing the game that would be a dungeon. And back then we had to have a huge imagination because this is actually what the game looked like, right? So, well, it wasn't exactly as the cover promised. But I want to use this as some context to relate what I'm going to talk about. Just really briefly, a little bit about myself. I'm a cloud advocate at Microsoft. If you're not sure what that means, feel free to stop me afterwards. I'll be happy to explain it. We've got so many terms in the industry right now, it's hard to keep up with that. I've been professionally developing for a capital really long time, so I'll just leave it at that. I've written a few history books. I think I released a Silverlight 5 book about 2 weeks before everyone figured out that it was going to die. And I released a Windows Runtime book just a few weeks before that platform shifted. And so as a result of that legacy, I have a lot of developers ask me to write a book about JavaScript. So figured that out. So I was a former MVP. I joined Microsoft, so you can't be an MVP in at Microsoft. I try to follow a 100% plant-based diet, but I'm sure that something in the food supply sneaks in there, so I say it's slightly less. And this is how you can get in touch with me, either through Twitter or direct through email. Happy to take your feedback and suggestions. Just a fun fact, actually my ancestors are from Norway. They came from a town called Likness with one S. And I guess at Ellis Island, an extra S was added. This is my first time in Norway, so I plan to come back and visit that town. What I want to cover today is level set, get on the same page of serverless. It's one of those terms we can't take for granted because no one can agree on what it means. Talk about durable functions, hopefully throw a lot of code out there that makes sense, and then we'll have some time for Q&A afterwards. So the first thing we'll tackle is what is this amazing, newfound, everything should be called serverless, right? So let's talk a little bit about how we got to serverless. I think a lot of us are still familiar with the physical servers that we own everything. This was early in my career. Basically, I had to worry about power, how to get access, how to install the operating system, how to patch, keep things up to date. There's a lot of responsibility for that, a lot of late night calls, a lot of weekends keeping things up. Fortunately, infrastructure as a service came along, and this abstracts the hardware out, and we're pretty much responsible for the operating system and everything on top. One of the best things that came out of infrastructure as a service courses that paved the way to bring workloads to the web. So I can take my virtual image and I can run that workload in the cloud. Then we have platform as a service. This abstracts everything but the platform itself. So as a web developer, if I'm building a web API, I can focus on my web project and not have to worry about maintaining the operating system. Does anyone here work with IIS server out of curiosity or has in the past? So a few hands I can see through the blur of lighting. So we don't have to become experts at IIS. It's fully managed for us, so we just focus on the web project and deploy it, which is great. Serverless takes that one step further, and it abstracts the platform, and we focus on the code. And I'll show you what that means in a second. I like to do a little bit of a gut check. This is not an industry-defined standard, but this is what I proposed as an idea of what separates serverless from fully managed. And the one that's most controversial that people tend to disagree with me on is this: do I only get billed for active invocations? I think a lot of times what people market as serverless is really fully managed. And the distinction here is how does the code scale And am I paying for something if I'm not actually using it? The way Azure Functions works, which is a serverless platform on Azure, is you're billed based on how many times the code is called, and then you're billed for something called a gigabit second, which I'll come back to. It's actually, some people explain it in a complicated way, but it's pretty straightforward when you see it graphed out. This is what it would take for 1 million invocations, taking up about 128 megabytes of memory for a second each, which is pretty slow, right, if your function takes a second every time to call, and that's free. If we have more activity than that, let's say we go up to 5 million, in the pricing calculator, it's like $4.40 US, so it'd be, I don't know, what, 300 something. Is it Kron? How do you pronounce it? Anyone? The local currency? Krones? All right. Okay, yeah, maybe 40. Yeah, that's right, 40. 400 people are going, man, this is getting expensive quick. So why serverless? The first thing is microbilling. There's potentially a lower cost, and we'll talk about that distinctiveness in a second. But if I'm not running workloads, I'm not paying anything. If I have a massive amount of workloads, I'm paying for those, but I also have a massive amount of users, so it's kind of a positive. I have less server to worry about. We'll look at that. I have elasticity, so the platform is managing the scale for me. And in most cases, we end up with a rapid development lifecycle because there's features of serverless that make it easier to develop. So Azure Functions is code and events. And if you're curious and you've never seen where the logo for Azure Functions came from, it's been revealed to you right here, right now. The secret is out. Azure Functions takes a set of events, and every time I'm going to demo a web API because it's the easiest thing to demo, but it does a disservice to functions to imply that it's only APIs. Services can run based on triggers, based on events like file uploads, based on events like messages in a queue. So there's a lot of reasons why a piece of code might be executed. That code is called, it does something. One of the benefits of this platform is most cases you can use a language of your choice and a runtime of your choice to build that code out. And then you have side effects, you have outputs, you might manipulate a database, you might return a value. So that's it at a very high level nutshell. Here's an example of a function. We basically attribute it. So we're tagging this method is going to behave as a piece of function code. Then we have a trigger. And again, there's multiple triggers. In this case, it's an HTTP trigger. Notice I'm not setting up a web controller. I'm saying, here's how I want you to call my code, letting the platform take care of the rest. I have bindings that make it easy to interact with other resources. In this case, I have a binding for a queue and a binding for a table. And then I'm using dependency injection to have a logging mechanism injected for me. In the body of the function, I can do something like take the trigger, and it hands off all the information I need. So I get that request object, and I can parse it out and figure out what is the component of the request. If I want to add something to the queue, I can use that binding. Notice that I'm not spinning up a new class. I'm not parsing a connection string. I'm not doing anything else but taking that attribute that was passed in, that parameter, and interacting with it. And then this is an example of me working with the table. The table's handed to me, and I interact with it. So when we're working with Azure Storage, the nice thing about the serverless platform and everything I'm going to show you today is that there's a fully capable local environment that you can debug and run and execute without connecting to the cloud. There's a storage emulator. Azure Functions are backed by storage for things like logging, and automatically has access to things like queues and tables that come with storage. And then there's a Storage Explorer that's a cross-platform tool that allows you to interact with that storage, both locally and in the cloud. Anyone here work with Storage Explorer, by the way, have familiarity? So most people are familiar with that. So for those of you not familiar with functions, I want to do a really quick demo and just do a live creation of a function. What could possibly go wrong? I'm just going to keep the default app. I'm going to trigger it from HTTP. I'm going to make this anonymous so I don't have to worry too much about authentication or authorization. And this is going to spin up a new project, and it's going to create a function app. A function app can have multiple functions in it. Think of a function app as a unit of scale. When your application is scaled out, it scales out at the function app level. So whatever I group into this project is going to scale together. So if I have related logical endpoints, that's what's going to drive the decision to make these multiple methods in a single function app versus separate. Now this is showing you what I showed you in the slides. It's just basically echoing a name back. We're going to make it a little more interesting. I'm going to turn it into a proxy. Then I'm basically going to say if string is null or white space, the name that's passed in, return new bad request object result, need the name. I've always been very thorough with my error messages. And then what I'm going to do is something a little bit different. I'm going to actually create a new client. And this is my favorite borrowed feature in Visual Studio. Pull in the usings automatically. Actually, I did that incorrectly, but we'll get around that. And then I'm going to do await text equals, no, let's do txt var text equals await client get string async and the name. So I'm assuming that we've passed in a valid HTTP request. I'm just saving typing. And then I'm going to assume that that comes back okay and just return the text. So we're going to go ahead and start this without debugging, so there's a little less overhead. Now what this is going to do is it's going to launch the function app host. This is a cross-platform host. It'll run on Mac, on Linux, and on Windows. And it's the same host that runs in Azure, so I'm getting the same experience. And here it's parsed out my function app, and it found an endpoint for me to interact with. So I'm just going to grab this endpoint. We'll copy that. Let's come over to a web browser and paste that in. So the default paste is going to basically come back and tell me it needs the name. That's fine. This is the perfect place to insert a shameless plug for my blog, blog.jeremylikness.com. And it goes out and spins, and we're over conference Wi-Fi. There's probably, and boom, we get the source for my blog that right now is hosted on Medium, but is being migrated to Hugo. So this HTML will be cleaned up a lot more. But that's it. That's a function in process. So let's go ahead and maximize this back and close this out. So that's just a really short demo. Of course, I'm not here today to talk to you about functions. I'm here to talk to you about durable functions. So setting the stage for what I just showed you, the triggers that can invoke a function are many. These are not all the triggers. These are the most commonly used ones. The bindings that make it easy to work with code that you put your side effects into or update or manipulate are also many. And the billing, I talked about the gigabit second. The billing is pretty straightforward. Left to right is time. The vertical axis is how much memory. And we get billed for the area under the curve. So you can imagine that if something takes a really long time to run under this runtime, it's going to be more expensive, and there are other models to host it, but for the serverless consumption-based model, that's how it works. And also if you consume a large amount of memory, that also raises the cost, and that can help drive some of the decisions around whether or not you're going to use serverless. So what's interesting is a lot of times we have processes that are a long duration, but they're not really a lot of compute time. Now, in the function I just showed you, I'm getting billed for the time it's waiting for my website to return the results, and it just doesn't seem fair that if a website is really slow, then I'm getting billed for that. So that's one of the side effects or issues with the functions out of the box. A lot of times we have this idea that we're computing and then we're waiting for something and then we compute, and the actual compute is really fast, just the duration takes a longer time. So what are durable functions and how do they help us in this scenario? Well, there's Challenges with serverless, specifically Azure Functions out of the box. One is that there's no state. You have to manage the state yourself. So if you're trying to do a workflow and keep track of state and come back to things, there's a lot of effort involved. Things like asynchronous dependencies then become complex. Let's say I'm waiting asynchronously for something to happen, then I get that result, have another asynchronous. That's either going to be long running or you're going to be jumping through hoops to optimize that. There's also no state. Did I mention that? There's no state in the functions. They're designed for a shorter duration. That's how the billing model is out of the box. There's also no state. I'm not sure if I mentioned that. And putting together complex workflows is, to put it bluntly, complex. So sorry to be redundant, but that's the reality. And there's no state, by the way. All right, so what's still hard with this? Well, one of these would be what I call asynchronous sequential operations. Go out, get something, wait for it, come back, get something, come back. That's going to be difficult to do in a cost-effective way. Even more difficult is fan out and fan in. So I want to build a search engine aggregator. You put in your search term. In parallel, I want to go out to Google. I work with Microsoft, to Bing, then Google, and this is in parallel. Alta Vista, Lycos, some of the other servers. I get the results, pull them back together, call another function to process it. So that's another pattern. I may have this idea of external events correlation. So let's say I have a process that has 3 steps, and I want to raise an event to say step 1's done, step 2's done, step 3 done. How do I manage that in code and in serverless? What if I have something that's long running, that's doing something interesting that I just want to poll every once in a while and ask it, where are you at, how are things going, etc. So this is a process that's ongoing, and its sole purpose is to provide me an endpoint to get information. Maybe I have a process that I kick off as a job that's long running, and I want to get the status of that job and allow it to continue running, but I get that status in an asynchronous way. And then what if there's human interaction? Let's say that I have a customer service ticket come in, and I basically want someone to interact, so that triggers an event. But if they don't interact within a period of time, I want to automatically escalate that. How do I correlate those two things, that timeout wait and that human interaction? So durable functions are designed to simplify everything I talked about. They're actually based on something that's an open source framework called the Durable Task Framework that exists. You can use it in .NET applications today. There's just a specialized version of that used to extend Azure Functions on the Azure platform. The way it works is we start with a standard Azure function. That function kicks off an orchestrator function. The orchestrator is what's managing the workflow. You can have multiple workflows. You can also have nested workflows, and we'll look at that. The orchestrator function itself has some rules that we'll get into. So it's basically just managing the workflow. The steps within the workflow are fanned out to what's called activity functions. Activities are what actually performs the work as part of this orchestration. So it looks sort of like this. The client kicks off the orchestrator. There's activities. I may have a sub-orchestrator that has its own activities. So some of the rules that bind this whole engine is this idea of reliable execution. The way the orchestrator works is when it goes to sleep, if something interesting happens that wakes it back up, it replays the data to get to a certain point. So it needs to be reliable in that the same input has the same output, because it uses these checkpoints that are at every time it's waiting for something to happen, there's a checkpoint it saves and plays back to. So you need to have that predictable workflow. It saves a history so that it can manage these checkpoints. It has to be deterministic. If you do something like if I roll dice and randomly go to one activity or another, the orchestrator is going to fail because it has to have a deterministic path, and we'll talk about how that's managed. But there are non-deterministic steps, right? You have side effects. You're going to update a database. You're going to send a message. You're going to have information that comes out as a result. So those are encapsulated within these special types called activities. The orchestrator function needs to be non-blocking. It runs single-threaded for optimization. So if I do an iteration or I do a thread sleep 10,000, I'm basically halting all of my orchestrators on that particular process. Because of this, we don't await anything just inside the orchestrator that's not part of the orchestrator client. The client provides things that you can inspect, things that'll kick off activities. Those are what you await, and that's where the magic happens, that it automatically saves state. And I'm setting this context because we're going to go into code, and it'll make a lot more sense when you see it in action, I promise. We can do things like have infinite loops, but I mentioned earlier that there's an orchestration history. So how do we manage that? The orchestrator actually has a special function called continue as new that allows that loop to keep running and flushes the history periodically, and you determine when and how that happens. And the unit of work and what we're doing is a durable task, and I'll show you what those look like. So this is my vision. I set out to create a text-based adventure game. Turned out it was pretty simple. Basically, you join a game. You have 2 minutes to confirm that you're really committed to playing it. If not, you're killed. I'm sorry. That's just the way it's set up. You pick up a weapon. You slay a monster with the weapon. The monster drops a treasure. You get the treasure. You win the game. Hopefully, you do that within a reasonable time frame, but that's the whole point of this talk, is long-running stateful workflows. So what seems pretty simple can actually look complicated when we put boxes and lines together and say, I'm an architect now, I've done a diagram. But seriously, this is the new user flow. What it's going to do is kick off some parallel jobs to create the universe. Then it's going to kick off a monitor that checks, is the user still alive, is the user still alive, etc. It's also going to kick off an orchestration waiting for the confirmation. So if we look inside that confirmation is going to wait for that manual intervention, yes, I'm committed to playing the game. Or if 2 minutes is hit and there's no confirmation, it's just going to kill the user, unfortunately. There's the user monitor checking to see, is the user either dead or have they won the game? And then there's a game setup. The game setup's sequential because we're dealing with table storage, and we need to do something like take an inventory item, put it on a monster, put a monster inside a room, put a user inside a room. So instead of dealing with complex concurrency, we know that that user is one workflow, so we'll do that sequentially. And then finally, we have a game loop that is expecting 2 things to happen to win the game: killing the monster and grabbing the treasure. So it's waiting on those 2 events. So to get started, there's an extension. It's probably a newer version now, but this is the screenshot when I took it, that you basically pull in a NuGet package, and that pulls in the version of the durable task framework for Azure Functions. And then this is a standard Azure function. This is kicked off by an HTTP trigger. So it's very similar to what I just showed you. However, if we dissect this further, we'll see that there's an orchestration client that's injected. This is one of the bindings that then allows me to control and interact with orchestrations. And I can do things like start a new orchestration and pass it a piece of information to uniquely identify that orchestration. It gets an ID, but we probably have some business data like a inventory item number, or in this case, a username that makes that workflow unique. And then that await doesn't successfully wait for that orchestration to run. It just schedules it, kicks it off, comes back, says it's scheduled, you're good to go. So you're not blocking your function call. So let's start a new game. What I'm going to do is I've got a console that's running in the background so that I can send some messages to it that we monitor. So I'm going to run that. It's a very simple connection string connected to local storage right now. And then I'm going to go into my durable dungeon, and I'm going to start this. And this is going to build and scan it. And this time, when it looks inside the project, we're going to see it finds a lot of endpoints, a lot of workflows and endpoints and APIs. Has anyone here worked with HTTP REPL, by the way? Show of hands. So this is an easy way to interact with endpoints. It's a global tool for .NET Core. And what I can do is use it to post and get and interact with APIs without pulling up the UI for Postman, for example, which I'm sure a lot of people have used. So what I'm going to do is just set the base URL. That's how we start. And when you set the base URL, in this case, I don't have this augmented with Swagger, but if we did, it would actually pull Swagger and figure out what the characteristics of the API are. But in this case, I'm just going to say post new user. So that's a function endpoint. And I have this configured to open up Visual Studio Code for me to write the payload. And a new user just has a name. So we're going to give the name Jan. We'll save that and close it. And we get this 200 OK. If we come over to our console, we can see that there's a gigantic indigo basilisk, a spacious room was prepared, there's a hefty morning star, a magic diamond, so we have all these cool elements, and now there's 2 minutes to confirm we're ready. So that kicks things off. So let's talk about what happened. First, the orchestration client. This is able to start a new orchestration. It's able to get the status of a running orchestration. It's able to terminate a running orchestration, so if you have a management console. It's able to raise an event, so inform an orchestration that something happened, and it can also purge the history for an instance, so you can do cleanup routines. So the first thing this create user thing did was these parallel functions to create the universe. So I want to show you what that looks like in code. I'm going to come back over here. And first we have these dungeon functions. This is what kicks things off. Let me just pull this in. So for new user, we have an HTTP trigger. We've got our console. We've got a table reference. And we've got an orchestration client. So this is pulling out the user. It's going out to the table to check to see if the user already exists. If the user exists, it says we got a problem, there's already a user. And then it's kicking off 2 workflows. So this new user parallel functions and this user monitor workflow. So the ongoing monitor for the user. And then it just says, okay, I think everything's fine. So when we look at the parallel user workflow, I've got these separated into different files. Here's the main orchestration piece. So notice that it's triggered with an orchestration trigger. Just like we had an HTTP trigger, this is triggered with an orchestration trigger. I'm getting the username, and then here's a list of tasks. Create user, create monster, create room, create inventory. And I just do an await task when all. Keep in mind that each of these tasks were called off of the context. Remember I said we don't await for anything that's not on the context. And then when it's done, it calls a sub-orchestrator that kicks off the confirmation workflow. So I'm doing that as a sub-workflow. So what that means is this parallel workflow won't end until the confirmation workflow ends. They're tied together. And this is just to demonstrate how that works. If we look at a given activity, these are the units of tasks that can have side effects. These don't have to be deterministic. So this is triggered as an activity trigger, gets a table and a queue, and this is literally just going in and creating a user. And the bindings make my code succinct and compact. It's passed in. I basically get a client, create the user, I'm done. We do a similar thing to create the monster, to create the room, and to create the inventory. So that's the parallel workflow. And it just automatically waits for all of those parallel functions to end, and then it continues through. So the thing it does as the sub-workflow is this user confirmation workflow. That's setting a timer, and then it's also waiting for human interaction. If we look at the code for that, I'm going to come into confirmation functions, and we've got user confirmation workflow. So again, this is kicked off with an orchestration trigger. We're getting the user, and I'm calling an activity to add something to a queue. Because remember, I can't await to add to the queue asynchronously myself because I'm in an orchestration. So I can wrap that in an activity, and that activity is sending it into the console just for information. Now here's how I'm doing a timeout loop. I'm basically creating a cancellation token Getting time off the context. This is what makes it deterministic. If I did date time UTC now, that would change with every run. If I get it off the context, it's consistent every time this orchestration flows through. So I get that, I'm adding a time span. I'm also waiting for this approval event to happen. And then I create the timer, and I'm waiting for either thing to happen. I either get the approval or the timer fires. So 2 minutes or an approval. If I got the approval, I cancel the timeout, confirm the user, and then I kick off this sequential workflow that we'll look at in a minute. Otherwise, I basically time out and I call an activity to kill the user. So if we look at our activities, I'm going to skip over confirm user for now. Kill user is basically just going out to a table, and it's setting the user is alive to false. It's a pretty simple way to kill the user. So that's what's in that workflow. Now, if we go back over to our console, I've been talking long enough that the workflow kicked off and Jan has died because I've spent too much time talking, my 2 minutes went up, and it's game over for Jan. So, having done that, this is another picture from the catacombs. Let's look at status checking and some of the internals of how we got to where we're at. So what I can do in my HTTP REPL is and I'm just going to steal this from a web page so you don't have to see me fumbling with typing. And we're going to do user, actually I will fumble with typing, user confirmation, user monitor. So we're going to get check status, part of the path is the username, and then user confirmation workflow. That's going to call out to the endpoint, comes back, it tells me that that's a completed process. And the other one is the user, user monitor workflow. Does a similar thing. If we look at the code for this is going to be in Dungeon Functions. Once again, the entry point is just a standard trigger, HTTP trigger. I'm checking on the status of this user. What I do is I have a helper job that sends out a query and says, give me the instances that have this workflow name and this user. And then it just simply queries the status and returns it. So that's how we can do that ongoing set of basically checking status and monitoring it. Now behind the scenes, a few things have happened. If I jump into my storage Explorer and I open up my tables, we can see that there's this Durable Functions Hub history, and that's a history of everything that's happened up to this point, which is quite a bit of history for a short time talking. And then we have these instances that show that there were a total of 3 workflows, and they're all completed. So behind the scenes, Durable Functions creates a set of control queues and a set of tables to keep track of history, store checkpoints, and ensure that the orchestrations are running correctly. And that's what we query behind the scenes. And then you can see I've created sort of the elements of my universe here. There's the inventory, there's the monster, and these are partitioned by user and then have keys based on what the items are. So that's a little bit behind the scenes for that. Now, just as an aside, one of the advantages you get from using Durable Functions is some advanced error handling. So you can use try-catch within your code. That's perfectly fine. As long as it's in a deterministic way, you're not rolling dice within the block. Any failure inside an activity will throw an exception, so the orchestrator will receive an exception from that. And if the exception's not caught, the workflow is going to end with a failed status that you can query for and look into. However, you can manage your activities. You can set up when you call those async activities without changing the code of your activity. It might be updating a table, doing something like that. You can set up retries, a retry interval, a back-off interval, a timeout. You can even create a function that it'll call back and say, should I retry again or not? So you have some flexibility with that. This is an example of what that would look like. Here we're saying if it doesn't work, try again after 5 seconds and try it a maximum of 3 times. And then we're calling it with that retry. And if you don't like flaky function passed as a magic string, As long as it's in something that you can access from types from the code, you can do name of, right? And then pass it as a solid reference. So let's look at sequential workflow monitoring with a user that we don't let die. Let's actually create a user that survives the process. So I'm going to come back to post new user. That's going to pop open Visual Studio again. And this time, let's make a user named Emma. Going to save that and close. So I get my OK. If I go to my console, it's showing me that it's created the user, and we're waiting for confirmation. So I'm going to go ahead and post that confirmation. So I'm going to post confirm user. And it's the same structure. I basically pass it the name, save that, and close that. If we look at our console, we see we've accepted the challenge, and now it's giving us some context. She's standing in a room, there's broken pottery, the user confirmation workflow is complete, there's a glowing mace, there's a glowing red gorgon, or a growling red gorgon, so glowing mace, growling gorgon, and Emma's alive but hasn't found the treasure yet. So let's walk through what happened when I confirmed. So the first thing it did was kicked off a sequential workflow. So we created the inventory, the monster, the room, but we didn't tie anything together until Emma made the commitment. The code for that looks like this. We've got a confirm user, which is just an HTTP trigger. And that's going to come in, and it's going to do some things like make sure the user's there, make sure the user's alive. If everything looks good, and it's got the confirmation workflow because it wants to know it's running. Remember, the workflow was waiting for either the timeout to fire or for that event to come that the user confirmed. This is how we send the message that they confirmed. We go out and we grab that client, so we give it the username. This is here. And the name of the workflow. When we grab that workflow, we just raise an event called approval task true. So that's what we did. We just sent to that user confirmation workflow and said, yes, they're approved. So if we go back to the user confirmation workflow, if it gets that message right here, so it's waiting for either the approval or the timeout. If it gets the approval, it's starting a new workflow called Sequential User Workflow. That's over here, and it's going to be a little anticlimactic after seeing the fan out, fan in. We're just simply awaiting in sequence. So we're saying basically put the user in the room, put the inventory in the room, put the monster in the room, give the monster the treasure, and now start a new workflow that monitors the game. So we only kick off that game monitor workflow if the user commits. And we can come back to our REPL, and we can do a check status. This time we'll do Emma. And the user monitor workflow is running because she's still alive. She hasn't died, and she hasn't won the game. We also now have a game monitor workflow, and that is also running. So speaking of that, user monitor workflow and game monitor workflow. I have two different long-running workflows to show you two different ways that you can do this with durable functions. I'm going to come back over to the code and go back into monitor functions. And the first thing we'll look at is the monitor user. So the monitor user comes out, makes sure it's a valid user, and it's checking. So this is an activity basically to see, did the user get the treasure? Did anything interesting happen? And it's just sending out information to the console based on that. If we look at the user monitor workflow, this is setting up an expiry time, and it's actually checking every 20 seconds, how's the game status going? So we basically monitor the user, while we're not timed out. So I didn't want this to run infinitely if someone accidentally left it on. So it runs for an hour. Hopefully we're not here an hour from now. So it'll time out automatically. And then it's just setting up a next check and creating a timer. So it says 20 seconds, let's check again, 20 seconds, let's check again. If we're an hour out, we're just going to give up. And it's check, check, check. If we time out, we end the function, and we basically tell you it's either timed out or it's done. And if it's done, it's because the user won the game. And this check right here returns a Boolean, so it's true if everything's done, false if it's not. And it'll be true if the user dies or if the user gets the treasure. So that's one way to do it. So that's on a timer. Every 20 seconds, how's the game going? There's another way that we can do this, and that's the game monitor workflow. And the game monitor workflow is waiting for two events, killing the monster and getting the treasure. So we just set up a wait for those external events, and we do a wait task when all. And it's as simple as that. It's just going to wait, and unless those two events come in, the game monitor workflow is just going to keep running. Now, I could have done a timer if I wanted to time out. I could also have another function that will go out and kill the workflow. But right now, this workflow is just perpetually waiting for those two events to come in. And we'll look at how those events come in a second. If we look at our table that was set up, now if we refresh this, you're going to see there's a monster, is alive true, and we've got some inventory items right here. So it's got a warm diamond. If we look at the room now is going to, if I scroll over, you can see that the user or the monster and the inventory item are placed in the room. So everything's tied together, and the game's in a state ready and waiting for something interesting to happen. I'm sure you're waiting for something interesting to happen too. So let's go ahead and end this game. We have a few steps to make that happen. First thing I'm going to do is have Emma pick up the weapon. So I'm just getting the template for this, and of course all this code is open source, and I'm showing you the walkthrough so you can do this on your own. And I'm just going to come back and do a reality check. It's a glowing mace. So if I'm going to post to my action endpoint, and my action is to have Emma get the glowing mace. So we'll save that, close out, and if we go to our console, successfully grab the glowing mace. You see that at the bottom. So the next thing we need to do is kill the monster with the mace. So we have a little bit more complex command here. I'm going to post to my action. This time I'm going to do a kill action. The target is a growling indigo, was it a basilisk? Growling red gorgon. And instead of the magic mace, we're doing it with the glowing mace, which I'm not quite sure what the difference is. Apparently the magic mace is a little more magical than the glowing one. That's my best guess for you. So we'll do that. We get an OK. We pop over to our console. So we valiantly killed the glowing red gorgon, and they dropped a worn diamond. So the last task, and I'll let everyone here sort out how a diamond gets worn, but it could happen. So we're going to name Emma, action get, and our target this time is a worn diamond. I was really hoping for the bloodied Commodore 64. That's my favorite treasure, but alas, the randomness did not align. And it helps if I close out so it actually posts. So we get an OK. And it says it's won the game, but what's interesting is right now the game monitor's done because it got its two events. Now you can see Emma's won the game. finally, Emma monitoring's done. So that kicked off a little later because that was on a timer. And now, if we look at our status for our different workflows, let's go back into our hub instances. We can see we had a lot more workflows for Emma, but everything is completed. There's nothing running. So everything's concluded and closed out. So I want to just show you how we raised the message, and then we'll cover a couple other points. So if we go inside to Dungeon Functions, this is where we have our actions. Actually, action functions makes more sense, right? I named these actually quite well. So this is, again, an HTTP trigger. And what it's going to do is it's going to take all the information in. It's parsing out, is the user actually there? Is the user alive? Does the monster exist? Is the inventory that the user is trying to get? There's a get method. If the action's kill, there's a kill method. And if we look at let's look at the get method first. So the get method is simply a method that I can call directly from within code. There's nothing special. This isn't a serverless endpoint. It's just an internal method that I'm calling to separate out code. But what it's doing is it's checking the target, seeing if the room has the target, grabbing the target. And the key thing to look at is if what Emma grabbed is a treasure, it's going to tell us that the user nabbed the treasure, and then it's going to go find that game monitor workflow, because there's one running for Emma's game. And it's going to raise the event got treasure. So that's the first event that it's waiting for. Otherwise, it's going to say target not found or try to get a target that doesn't exist. The monster logic also has to figure out, does the user have the weapon? Is the monster in the room? Did we name the monster correctly? Is the monster actually still alive? Because you could try to kill it twice and it'll come back with a snarky tried to kill a ghost. But if it's alive and everything pans out, it's going to do a similar thing where it's going to update the table, mark the user or mark the monster as dead, and then it's finding that game monitor workflow again, and it's raising that event kill monster. So it's signaling into the event that can happen. Now that's how that code works. There's another open source project that you can find, I'll link out to it, that's part of the Microsoft Ignite tour. This is a tour that was after the Ignite event. And we had a serverless module where we did a more corporate-focused example. And this is a SKU. And a SKU is an inventory item, and it has a lifetime. So you can add a SKU to a catalog, but then there's some expectations. The SKU needs to have its price correctly set. It needs to have a description. It needs to have an image. And it needs all of these things to happen before it can be active and visible in the catalog. And so that example uses a long-running workflow like this to wait for those events to happen. And it actually uses Event Grid, which is a messaging service, to send those messages in. And it just relays them. It gets the message, okay, the description was added. Let me find the workflow for the SKU and raise the event to the SKU that description was added. So that's how that workflow works. So as a summary of what I showed you with these orchestration contexts, we're only awaiting on tasks derived by the context. If we try to wait on something else, the orchestration will actually throw an exception because it'll detect that it's non-deterministic because you're awaiting something it doesn't have control over. There is a flag on the context that if you have something like you want to log something only the first time it kicks off, you can check is replay, and because the logging doesn't have a side effect except in the log itself, which it's not a side effect in the workflow or the state, that's acceptable. So if is replay will do this thing. You can kick off new orchestrations, but you have to do them inside of activities. And I'm not sure why they don't put this on the orchestration trigger, the ability to create a new orchestration, but they don't. So if you try to await and bring in an orchestration binding, you're not awaiting on the context, it's going to throw an exception. But you can have an activity that you await on the activity and tell the activity to kick off the orchestration, and that works fine. And date time is only real on your context. You got to get used to, if you're checking time, you check context, get UTC date, as opposed to date time now. So there's some advanced concepts that come around this. There is the possibility of cross-app communication. So if I have multiple orchestrators and different function apps, I can set up, and this is using a pretty straightforward HTTP set of requests. So it's using an HTTP endpoint basically to kick off another orchestrator, and then it's going out and getting the status. But you could use queues, you can use messaging. There's other ways to communicate between orchestrations. The way orchestrations work is there's a concept called partitions that orchestrations are scaled across. There's a default of 4. You can configure it up to 16 on a host, and then you can also run multiple hosts and scale across hosts, and there's guidance in the documentation for that. You can also throttle concurrency, so you can determine how many requests a certain set of partitions can handle at the same time. And then there's this concept called extended sessions. Now, I talked about the checkpoint and the replay. So every time it's coming in, it's replaying all these messages up to a certain point. You may have a process that times out in 30 seconds, and it's doing a check and doing that. Well, if you don't set up an extended session, it's still going to replay even in that short period of time. If I can figure that to be an extended session, it'll say, okay, what they're telling me is we can keep this in memory and just wait in memory and not hydrate everything to disk and basically override the default behavior. So you get less history and you get a little bit more performance out of that. Then I talked about high availability. Basically, everything is managed through a storage account. So the queues, the backing tables are in a storage account. You can create a globally redundant storage account. So that redundancy is built into how you set up the storage account. You could have multiple orchestrations in different regions using a storage account that's not globally redundant, and then that becomes your point of failure. But if you have a geo-redundant storage and you have geo-redundant orchestrations, they're all kept in sync because they're talking to the same storage client, and it's handling that replication behind the scenes for you. For performance and scale numbers, this is more, it's not as interesting in the talk, but I wanted this in the deck for you to refer to. There's a performance target of 5 sequential activities per second per instance. This is assuming that it's a reasonably returned activity. Obviously, if the activity itself takes a minute, but if you have a return directly from the activity, this is the level fan out 100 per second per instance. This kind of helps you based on the volume of controls you're bringing through durable functions, figure out partitions and if you need multiple function apps running. And then you can actually unit test these. Now this is a little bit dated. I apologize for not updating this, but it was a rabbit hole I didn't want to go through at the last minute. But the newer version actually goes away from these base clients to interfaces. But originally, if you're using the version here, you can mock a base class and you can set up expectations. You can create a mock logging mechanism. You can create a mock orchestration, status response. So you can fully unit test it. And the newer version uses interfaces, so you even have more flexibility with mocking those interfaces. Now, before I dive into the summary, I did create a utility because all of these are APIs that you can access over HTTP. So I created a very simple front end. I'm going to take full credit for the UI design. I added a couple of fonts and padding tags myself. I'm very proud of this. I don't want anyone to freak out if you look at the source code for this, because this will run and give you a front end that interacts with everything. But if we look at the code, what you're going to find is there's a disturbing lack of any fancy JavaScript framework. It's just using vanilla JS. So it's just straightforward JavaScript, and we're using these things that some people who have lived and died in Angular and React might not even know there's a Git element by ID. But you can walk through this code base. I tried to keep it simple. But this basically, it's showing the status of the different workflows. It allows me to enter a user. So I'm going to use the handle that I used to use when I played Doom and Quake back in the day, which was Nicodemus. And when I start typing it, it starts monitoring. And they turn gray because it's unknown status. Right now, I haven't done anything interesting. So I can create a new user, and all of a sudden you see the user monitor and the run user parallel workflow. Those kick off, and the universe is now waiting for Nicodemus. So it's waiting for the confirmation. So I can come here and notice that the user confirmation workflow kicked off. So I'll click confirm, and now these turn red because these workflows are done. And now we've got the user and the game monitor workflow running. And we've got some context here. We can see the description of the room. There's a moaning indigo troll. So that would be interesting to put up with, right? All right, we're getting better with the treasure, though. There's a Magic Zork trilogy set, which I'm pretty excited about. And we're back to a glowing axe. I'm not sure what that's all about. But let's go ahead and get the glowing axe. Okay, now I'm holding on to the glowing axe. So now I can kill. And I could say something with something else just to show you that it actually handles these cases. Action failed user doesn't have something else. It only has the glowing axe. So let's go ahead and kill the moaning indigo troll with the glowing axe. And it drops the Magic Zork trilogy set. So let's get the Magic Zork trilogy set. And we won the game. So this code will show you how, with all those endpoints that I was manually posting to, you could architect an application around those endpoints and workflows and work with them that way. So to recap, this code gives you examples of the asynchronous sequential workflows, fan out and fan in, external eventing, there's a couple examples of that, a long-running game monitor, a long-running API. That game monitor runs for a long period of time, but you can poll it and check status, and then that human interaction, that timeout and escalation. So all these elements are available. I'll actually tweet out the link to the full deck, but these are the main links for what I covered here. It's the emulator, the explorer, the durable functions, and if you go to the GitHub repo, that repo has step-by-step instructions to set everything up and walk through that. We've got about 3 minutes, so what I'm going to do is go ahead and close out, but I'll stay for any questions that you have. You can always feel free to email me and talk to me. Thank you once again for spending the end of your first day at NDC with me. I appreciate everyone.